Okay, so here we are, right? Before I move on, I want to say 2 or 3 things about quicksort and partition. So first of all, when we do partition, you don't have to write this because you already have it. So we have this drawing here, and we have this last value. That's the pivot value. Eventually, this is going to be placed where it should be placed. And then we're doing our thing in here with this is smaller than V, bigger than V, and unprocessed. The one thing I want to talk about today is, very briefly, this idea of peak V. So peak pivot value V, which is A of n, right? The last element. So we talked quite a few about how random this is. And we said, what? If you shuffle the array in advance, right? Then this V, even though you go down the recursion a few times, is likely to be a random value. Suppose I don't shuffle it in advance, right? So I don't have that. But I would like this to be a random value. How can I do that? So if I don't shuffle the array in advance, but every time I'm in partition, I say every time because quicksort is a recursive function, so it's going to come down to partition much more than once, right? A few times. How can I say this V is random?
I can pick a random index and take a value and just take it to that.
Right. So this can be done by doing what?
Picking a random index.
Right. Before doing this, which is what I need, I can say, how do you make a random A of n? Well, you do that by saying pick index I at random, index, right, from 1 to n, and then do swap of A of I with your value. How long does this take? 1. So just I want to point out something that if you don't want to follow that theory with shuffle the array and how random things are, you could quite easily pick a random value in the middle of partition if you want to. That's one thing number 1 that I want to talk. The other one, last time we said prove that if you shuffle the array in advance, so that's 1, 2, if A is shuffled of A once in beginning, prove that every B equal A of last in all partitions or I should say capitals. This is the partition function. All partition calls is random within its chunk. By chunk, I mean the current call. Okay, that's what we talked about last time. Show that if you shuffle one in advance, every time I get to partition, that last value, it's one of the random values in that set that we're looking for. It's not an easy proof. And I want to add one now, part 3. So this is the exercise. Was another question, how to shuffle in linear time. So at least two of you came to office hours and proposed a shuffling procedure. Here's the procedure, I think, if I remember it correctly. So how do I shuffle an array A? I think the procedure you guys were saying was for I equal 1 to n, right? So that's going through the whole array. Then say find an index j, which is random index integer from 1 to n, might be I, right? So it could be the item itself, and then swap a of I with a of j. That's not my creation, don't blame me. Two people came to the office hours and asked, how about this? So let's do two exercises based on it. Let's see how you guys do. One exercise here is every permutation of A possible? In other words, if I run this procedure, I'm going to get an array that's a permutation of the original array, right? Everybody can agree that a bunch of swaps will keep the same values, just in a different order. I think that's easy to agree. My question is, how many possible permutations are there? N factorial. Is any one of these n factorial permutation a possible output of this procedure? Or maybe there's some permutations that are possible, and some that are just cannot come up out of this thing. And part B, if the answer is yes to this, or even if it's not, is every output permutation? If the answer is yes, every out permutation means all of them. Right? Equally likely. In other words, if I apply this procedure, do I obtain a random shuffle? Or is some permutation somehow much more likely to happen than others? It's a little bit beyond the scope of the class, and it's more mathematical than an algorithms class. But again, this is extra credit. It's not going to count for your homework points, but if you want to think of something interesting, get two exercises here. I think that has to do more with mathematics than algorithms. Okay, and the last thing I want to say about partition, this is not stable. We had this discussion with a little bit of a confusion that if you swap the values, it's stable or not. I think everyone's convinced by now it's not a stable thing. Okay, I want to recap one more thing. Yes?
For the first part, after we run quicksort once, will the next P be random? How do we choose the next P? The same
So
way?
this will have to happen on every partition call. This idea with swap the last one with a random one so that the last one is random, a random one of the array. This will be part of every partition call. If I don't shuffle it in advance, this idea of swapping is not just going to happen once. Every time I call, so this is for every partition. That for sure is going to ensure a random element, right? Because I know I'm not relying on some initial shuffling. I'm just saying every time I call partition, pick a random value, put it at the end. That's my pivot value, so it's going to be a random one. Okay. The other thing we need to recap to move on is that theorem that was saying if an algorithm does sorting and it's based on comparisons, comparisons means things like if A of some I, the algorithm will take some steps, but at some point it's going to be like, if A of I is smaller than A of J, then do something else, right? all these algorithms we looked at so far, selection sort, insertion sort, merge sort, at some point they compare elements. Quicksort, where does quicksort compare elements? Where is quicksort asking that question? In partition, right, when it's looking at the value, it's saying how it's compared to the pivot value, bigger or smaller. If it's bigger, do something. If it's smaller, do something else, right? So all those algorithms must have running time at least n log n, if they are correct. Correct meaning anytime you put the input array, you get back a source of 1, all the time. So what was the proof of this theorem? The proof was, consider a tree that was all possible runs of the algorithm based on comparisons. So the algorithm starts here, and then it makes some comparison, and then maybe makes a comparison in the beginning. These are the comparison steps. And it always has this chunk, yes or no, right? We said every run is one execution for an input, and corresponds to a path from root to a leaf in the tree. Right? Every time I run this algorithm with different inputs, I say if this happens, that's a comparison. Is the first bigger than the second? If it is, do that. If it's not, do the other thing. For different inputs, I'm going to get different runs, which means different ways to get from here to a leaf. At the leaf, these are my outputs, right? Output, 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 so on and so forth. Now, to be correct, it means the number of possible outputs has to be at least n factorial. Because there's n factorial possible outputs that could be correct, right? Given an input array of size n, it could be any order to be the correct one, so I need n factorial outputs. And I was asking you guys to prove as an exercise if the number of, in a binary tree, if the number of leaves is at least n factorial, prove that the depth of the tree is at least n log n. It's an easy proof to say if you want n factorial leaves in a binary tree, you have to have at least n log n levels. It has to do with at every level, if I get a full level, I'm duplicating by 2, I'm multiplying by 2, right? That's how binary tree advances, right? 1 element, 2, 4, 8, so on and so forth. How many levels do I need? Essentially, I need 2 at the depth, has to be at least n factorial, right?
Yes.
So I need that many leaves. So now, taking the logarithms, you get the depth to be, it's theta of n log n. And by the way, what's the depth? Depth of this running tree is the worst case, right? The worst case of this algorithm, the longest run, is the depth that's the longest depth. I mean, if it's a balanced tree, it doesn't matter which one it is. But if it's unbalanced, the worst case will be the step that takes the longest, which is the longest path. This is the worst case. So in the worst case, the running time has to be at least theta of n log n. That's the recap we need to move on. Okay? So how do we sort in linear time? Look at this theorem. Say you cannot sort faster than n log n, right? Clearly, theoretically saying, There's no way to sort correctly in more and faster than n log n. And we know what faster means. That's asymptotic notation, right? So we're talking about asymptotically faster. Doesn't mean just a constant times faster. We mean something that is the ratio between the running time we want faster and n log n has to go to 0, right? Is that limit? Remember the small o or the small omega, right? So that's what we want to do today. That's our last session on sorting in linear time. That's our job for today. So I'm gonna say conceptually, first of all, how can I go around this theorem? This theorem is like a bottleneck. It's a big rock parked in the middle of the road. Doesn't let me go through, right? It's n log n. So how can I get something that works correctly and this theorem does not apply to it? If I get an algorithm that works correct, this theorem is going to say you need at least n log n. Well, except for the fact that theorem says based on comparison. So one way to go around is to say not based on comparisons. I'm not saying that's necessarily possible. I mean, it is. We're going to see today. But obviously, if my algorithm is not based on comparisons, at least I have a chance for this theorem to not apply. Good. So we're going to do that. What else can I do?
Reduce the size of the search space from factorial n to something
No,
like
I mean, the array is always of size n. The input array has size n. So of course, for smaller arrays, I'm going to get smaller running time. But we're talking about an array of size n. The other thing that's going on here as a requirement, so one is to apply the theorem comparisons. Maybe I can abuse that one. I can get around by not doing comparisons. The other one is that this is a worst case analysis, right? So this theorem doesn't say anything about the average. What it says is the worst case. It says in the worst case, you must have a tree or a run or a path that goes down n log n levels. So on comparisons, so based on comparisons, theorem will apply. So the theorem will say what? The worst case has to be, you can't cheat on the worst case. That's what the theorem is saying. But maybe I can get an average case better than n log n. Right? So maybe I can get the average case at least n log n. At least something else. Sorry. Smaller strictly. So asymptotically smaller than without n log n. Can I do that? Is it possible that the worst case it's n log n like the theorem says, but somehow on average I do it faster? That's a question if it's possible or not beyond the scope of our course. We're going to answer a slightly smaller question today, which is yes, we can do that with an assumption. So there's the bigger question, can you do it in general without this assumption? That's a harder question. But for us today, we'll say, yes, you can do it. We can sort in linear time. Let's say, yes, linear time with assumption that values are A of I, right? Those are the values in my input array, are uniformly distributed in range. A range is usually something like some continuous space that's from mean to max. When people say range, they mean typically an interval. And sometimes they say integer range, that means only the integer in there, or rational range, only the rational numbers. But typically when people say a range, they say from min to max. Now everybody knows what uniform means? It has to do with the density that says you can't have a lot of values packed in a corner of the range or in a value, around the value, and then some other chunk of the range empty or very sparse, right? Uniformly distributed means as n increases, so if you look at the range here, right? What the range says, every time you pick an interval in the range, so say I pick the interval from A to B, A is smaller than the mean, smaller than B, smaller than the max. It means the probability for one of the values, sum A of I, to be in the interval AB has to be approximatively, to be uniform, right?
Yes.
The probability to get something in here has to be about the size of
The interval.
that interval divided by the size of the whole range. That would be uniform if every single chunk contains roughly that many values proportional, that's the length of the chunk divided by the length of the range. Many distributions do not follow the uniform, like Gaussian distribution. Gaussian distribution has some mean, and a lot of values are close to that mean and not far away. So how do we do this? How do we, still based on comparisons, cheat on the theorem and get an average case that is linear? The worst case will still be pretty bad, the worst case. But under the assumption that the values are uniformly distributed, that assumption has to hold better and better as you get more and more values, right? If you have 3 values, what's uniformly distributed? You're going to look at those 3 values and say, maybe they were uniform. But if you have 1,000,000 values, it's quite easy to tell if they're uniformly distributed or not, because you can look at those 1,000,000, if they all over the place, they're uniform. If they dense in some parts of the range, they're not uniform, right? Hands up who's with me so far. We got a setup, right? So anybody knows how to do this? Midterm question, right? Suppose I have uniform distributed values from 0 to 100, fixed range, right? Do something, sort them, so that on average, the runtime is linear. On average.
Can you use extra memory for the sorting? Extra array?
Let's say yes.
So if we know the min and max, we can make an array with the indexes of starting from min and ending at max. Then we can traverse through the array of the elements, and if there is the number which is corresponding to that index, increase it by 1.
Right.
Like
So I think so I think you're about to go here,
Yeah.
not based on comparison.
Yeah.
So he's talking about the first question. And he's assuming that the values in this range are discrete. He was saying from min to max, build a sort of like lookup array and go for every single values. I think he means min plus 1, min plus 2, right? But that's not the setup in here. When I say range, those could be real values. So how many possible values are from min to max if they're real values? They're infinite. You can't build a lookup for every single possible values if those are, say, rational numbers or real numbers. Right? Computers don't really understand real numbers like we do. They need a representation. A representation is finite in decimals. So how many decimals you put, even if you give it like 20 bytes for each float, it's still a fixed number of decimals, which makes them rational anyway. But apart from that, what I mean to say here, those are real values, right? So keep your thought for half an hour, because I'm going to ask the question again in here, for a discrete range. let's just say this right now, discrete range. Discrete range is the one that it's fixed and it's like integer, like mean plus 1, mean plus 2, up to max. It doesn't have to be integers, right? I could use something like every quarter, 0, a quarter, a half, 3/4, 1, 1 1/4, 1 1/2, 1 3/4, 2. Like I can partition the range more granular. Doesn't have to be integers as long as it's finite. Right? So we'll get to there, but I want to solve this problem first. Anybody? An idea? Well then, let me put the name. Maybe you guys can figure out the idea if I just say the name of it. Right? I'll say the name and see if anybody knows the procedure.
Buckets or
Okay?
Bucketing.
So how does this work?
create buckets.
Create buckets. Very good. So buckets go from mean to max, of course. That's my range. Here it is, right? So I'm going to create a bunch of buckets. How the buckets should be paced? Equal. Why do you think they're equal? Because my distribution is uniform. Okay? So I have a bunch of buckets here. All right. I'm going to do this with an example. So let's say my array here is, let me see what I need. 1, 2, how many buckets I have here? I think I have 10 buckets. 1, 2, 3, 4, 5, 6, 7. Let's add 3 more. 1, 2, 3. Max, let's say the max is 1. This is max. This is an example, so it works for any range. Mean, let's say mean is 0. So now I have 10 buckets here. If this is 0, that's a 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. Right? So I got 10 buckets. Let's just call it K, but we say K equal 10 in here. Buckets. Right? For a range that is 0 to 1 range. Here's my array. The array is 0.78, 0.17, 0.39, 0.26, 0.72, 0.94, 0.21, 0.12, 0.23, and 0.68. This is my array. What should I do first? So I designed the buckets, right? So number 1, design K buckets. I didn't tell you what K is. We'll figure that out later. Then what's the next step?
Traverse the array.
And do what?
Put them in the bucket.
Put item in the bucket. So traverse, you say traverse A, put or assign. We're not really putting as in take it and maybe assign somehow, right? Assign each A of A value to a bucket. Is that a unique bucket the one is going to go into? Yes. So let's not say to a bucket, let's say to its bucket. So 0.78, where is this one going? This one is going here. Where is 0.17 going? It's going here. 0.39? 0.26? Here? 0.72? Here? 94? 21. Here. 12. 23. And 68. Right? I think everybody can see that. Now, how do I make this assignment? Do I start like in insertion sort, start at the bottom, take this 72, starting here, compare with this, if it's smaller, move it, if it's not, don't move. How do I actually assign things to buckets?
Divide the bucket size minus 1.
So you're saying the right bucket, if I'm putting A of I have some value, A of I, V. What is the bucket? Bucket for A of I, or bucket for I, right? Is going to be what? Can I calculate it directly?
Yes, you have I.
Divided by minus 1.
I say I take the value A of I,
Divided by
divide by bucket size. That's what you're saying?
Minus
Max
one.
minus 1.
So what do I do?
Buckets.
Range.
So A of I, take an example, 72.
Into 10.
How do I determine? It's enough to determine one edge, right? If I know it's the bucket after 0.7, I know the other edge is 0.8, right? So how do I take 0.72 and get this edge, 0.7? Can I do it in a constant operation, or do I have to play with values?
Second constant.
Based on the
So I have to do this minus mean, right?
Divided by max.
Divide by
Max minus min.
Range by range.
maybe we also need some ceilings. How about we leave it as an exercise? This is a 5th grade thing. You should know how to do it by now, right? So how can I take a value and place it directly into the right bucket? Remember, a bucket as an ID, it's enough to get one edge right? Because we know where the other edge is. We know the bucket size. If this is some value, V plus bucket size is the other edge. The buckets are uniform. So it should be easy to do it directly from the value without any searching whatsoever. So this should be O. Good, so I've got my buckets. I got every element in a bucket now. What do I do next?
Traverse the bucket.
Sort
and-
each bucket.
Sort each bucket. I'm so happy that you guys could figure out the procedure if I only say the name. You know? So that's what happened. I say the name and you figure out the procedure. See? Okay, sort each bucket. Let's say that that's a brute force sort. We don't care about the running time. So that's going to be, say, using, I don't know, insertion sort or selection sort. So insertion sort. Something simple. So that's going to be, what kind of runtime it's going to be? If I use a naive sorting procedure like insertion sort or selection sort.
Size of the bucket.
It's square, but square of what?
Size of the bucket.
It's not the size of the bucket, it's how many elements you got in. Right? So this is elements that got in, let's call it Ni squared, right? Where Ni is
Number of elements in the bucket.
number of elements
In bucket.
in bucket I or J, if I we use for the array. Right? So the question is that we don't know how many elements will go in each bucket. It's possible that all elements go to one bucket. Right? But that's unlikely. Why is it unlikely? It would be uniform if I have 10 buckets and all of them got here. That's not typically uniform distribution. Now, uniform doesn't guarantee anything. It's on average. So if I do it one time, maybe I'm really unlucky and all elements, even though they're uniform, were in one bucket. But on average, if I do this every day 1,000,000 times, cannot happen all the time that all elements are in one bucket. Those wouldn't be uniform. Okay. So, how many buckets we have? K buckets, right? So the running time for this last step will be sum for all buckets, right? What did we say? J. J are the buckets of theta of nj squared, right? Because we have to sort each bucket. Worst case, it's n squared of how many elements are in the bucket. So that's our runtime here. So now what do we want? We want this whole procedure to be linear. How do we do that? How do we get the procedure? Well, I think some things will be clear. It's a little bit of matter of design to pick this K. But then this is going to be, do I have to worry about this? So how big is this total? It's O of 1 times n elements, right? So this is linear. I don't have to worry about this step. Designing the buckets, that's probably not going to be more than linear, no matter how I design them. And then I have to worry about this part here, sorting the buckets. Okay, so the design of the buckets, we're going to say K equal N. So we're going to pick a K that's N. That's not the best K in practice all the time, especially if the distribution is not uniform. But let's just say for the theory argument here, we're going to pick K equal N. So if you don't know anything, you have a uniform distribution of values, you can just pick K equal N. You have to be a little aware of memory and data structures. Because you say K equal N, okay, how big is that N? I'm not talking about 1 billion, 100, 1,000. So don't go blind in practice with K equal N. But for theory, let's just say K equal N. Okay. So the design, so it's, the question here is this practical? Like if you want to implement bucket sort, would you really use that choice? We're not concerned with that here. We're concerned with the theory. Why is that overall a linear procedure? So we have K equal N. Designing this, keeping track of the bucket size will be an O of N sort of algorithm. So this is the problem right here, sorting each bucket. So here's what we need. We need an average case to be linear. That's what we want. So what we're going to do, we're going to come up with xij. This is a random variable that says it's 1 if what? Element AI goes to bucket J. And 0 otherwise. Who's in my data mining class? Memberships, remember? Right? We talked for 2 weeks about memberships. Yeah, if you're in that class, you should know this how it works by now. Xij is a random variable. It's not a 0-1 indicator flag that you can put your hands on. You can put your hands on once you see the values. Because once you see the values, you're going to know 0.17, it's array, what index is this? This is value 1, this is value 2, right? So x2, what bucket is this going to go to? 2, so x to 2 is 1. If one membership is 1, if this value goes to a bucket, all the other buckets will have a 0 because each value goes exactly to one bucket. How about this 26 here? It's x4, 3 equal 1, right? Because it's value number 4 goes to bucket number 3. How about this 21 here? 1, 2, 3, 4, 5, 6, 7 goes to bucket 3 equal 1. Okay? So xij, random variables, binary. They say is the item I goes to bucket j. For each I, there is exactly one j that's 1. All of them are 0 because it's going to go exactly to one bucket. Okay, so that's xij. So who's nj? Number of elements
Bucket J.
in bucket. J. How do I do this if I want to do it as a function of these random variables? Is the sum over all values in the array or all indices of xij, right? If I pick a bucket number 3, I sum up the xi3.
Correct.
How many of them are 1 indicates how many value end up in that bucket. So what is the running time for sorting buckets? Is the sum of xij square, right? It's nj square. That's how many elements are in the bucket square. Now the sum is over I here, like in there. That's for bucket I. But then there's another sum. This is this is bucket J. This is the over all buckets, right? Because I have to sort all buckets. Hands up, who's with me? So this is the runtime for sorting. It's a worst case because I'm doing a bubble sort or essential sort there, so it's something simple. This is time to sort the bucket times sum up over how many buckets I have. So now, what is this? When we say the average, what's this going to become? So xij, I can only see them when I see the values of the array, but on average, if I don't see the values, this is going to be an expectation, right?
Yes.
So over this random variables. What does uniform distribution means in terms of these random variables? The fact that the values were uniform distributed. What's that telling me about xij? Xij is equally like, for any I, Xij is equally likely to be any one of the buckets.
Correct.
Right? So the probability, so uniform distributed values means what? For every value, the probability of Xij being 1 is 1 over the number of buckets, right?
Correct.
Okay. Saying for every possible value, the chance of having it in any bucket is uniform by the buckets you have. Okay, so let's do some calculations here, right? How do we do this? I say this is the expected value of so first of all, the expectation, let's see if we can get it right here. So this is a sum over J. The expectation distributes on the first sum, right? In fact, expectations distribute over all the sums without any conditions. We know that? That an expectation over a sum of random variable, even if they are dependent somehow, the expectation distributes over the sum, meaning it's a sum of expectations. That's something you should know. So this is the expected value of sum of this xij is sum of xij squared plus sum of over aj xi times xj, I think. So imagine how you do this sum, right? You guys know the formula: a squared plus b squared plus c squared. A plus b plus c, everything squared. It's a squared plus b squared plus c squared plus d squared plus 2ab, 2bc, 2ad. So I think I need a 2 maybe here, something like that. I don't have a 2 here, I don't know why. Oh, I think because ij, it runs both ways. This would be AB and BA. You know what I'm saying? So let's write that formula down somewhere. If I have sum of xi squared is sum of xi squared plus sum over all ij, maybe those are different, I different j, xi times xj. Is that correct? That's for any variables, random variables or not. This will be the 2ab from the formula because there's ab and then ba. The sum, I could have wrote this as xi squared plus 2 if I put a condition I smaller than j here. Right? If I put it like that, AB will only happen once because it's only for A smaller than B. But if I don't put I smaller than J, it will happen twice for AB and BA, and then I get the 2. This recap from the secondary school here, how the formula works. Okay? So now, this is sum over the buckets. The expectation again is 2 things, right? So it's the expected of this sum. That's going to be the sum of expectations, I believe. So sum over I of expected value of Aij squared. Right? So what they do, this E went over this sum here, plus I can put the parentheses here, I think. What's going to happen here is the same thing, ij, the expected value of xi times xj. Remember that the expectation distributes over the sum. So sum of expectations or expectation of sum mean the same thing. That's a very nice property, doesn't require any additional condition, as opposed to the product or the variance that distributes only with independence assumptions. So now, xij squared is the same as xij because it's either 0 or 1, right? So if I square it, this is going to be sum over j of sum over I did I get this right? Let's hope. I say this is the same like that because xij squared, whether it's 0 or 1, is the same value, right? And these, I'm gonna assume independence here. So I'm gonna say independence assumption. This is the sum of x of xi, sum over ij, maybe this thing, times expected value of xj. That's another property that you should know. Expectation of a product is the product of the expectation, but not all the time. When is it for random variables? When you have independence. So I'm not asking you right now to prove that, but you should go home and say, okay, why is 2 random variables are independent? The expectation of the product is the product of expectations. You should recap that. I'm asking you now, why are they independent? Why can I make that assumption? Yes?
What is xi? Like we have xij as the random variable marking xi in j. So what is xi?
Oh, I made a mistake. Right. So I'm missing something here. You're right. So this is xij squared. Now what is this is what happened here? So I've got an xi something times xj something. I think this is an xik, right? Ik xjk, something like that.
It's kj.
Xkj? So hold on. What was fixed in here? J is fixed. So this is over 2 I and k is going to be ij and the other one is going to be kj. Because j is fixed of the sum index from here. And I'm only looking at this sum. So now this sum, it's going to be a product of two things that have the same j at the end. So this is ik, ij, kj, and then I have the sum in the front, ik, ij, k.
K here is not the size of the bucket, right?
No.
K is just any
Another
variable.
Let's choose another variable. Sorry, guys. Z. Is Z good? My notes are a little bit hand-wavy. Is that better? So I and Z are two of these indices in the array. J was fixed in here. J is the bucket. We should have called this K, I think, to be more consistent. But nevertheless, we look at this mechanically. I think people have got this sum correct. Now, where is Ij times Zj coming from? It's coming from the product of two of those things, right? And I get every product possible, perhaps, with a fixed J. Now, what happened here, I distributed the expectation over these sums. That's easy to see. You may have to recap why that is. That happens all the time. Except in here, I distributed over a product. Over a product, it doesn't happen all the time. We need independence between I and Z. So why is that? Why the two variables are independent? So because those are the buckets for two different values, we assume the values in the array are uniformly independent distributed, right? Independent meaning the probability of some value being in a bucket does not depend on the probabilities of the other values being in buckets. It's not like pick the first one. If the first one is bucket 1, the second one is less likely to be in bucket 1. Those are like coin flips. I take the coin the first time I flip it, I get something. The second value, it's another coin flip, independent of the first one, right? Yeah. So this independence means independent values in the array. If we have a dependency in the array, if somehow the first value of the second value have some influence over the third value, maybe how they do polling for the election. They ask some people, depending on those answers, they ask more people. That's not independent anymore. So now, what is the expected value of xij? That's easy, because we say uniform. So what is it? The average, so the sum over I. How much is the expected value of a binary variable is what? If xi is a random variable that's binary, the binary means 0 or 1, right? Expected value of xi is the probability that is 1, right?
Yes.
That's true for every binary random variable. Its expected value is the probability of being 1. Because expectation is value 1 times the probability 1 plus value 0 times the probability of being 0. So it's just that. So what's the probability of being 1? What's the probability for xi to go in that bucket? 1 over the number of buckets, which is n. We say somewhere use k equal n.
Yeah.
So you can say either n or k, so this is like that. It's the same thing. Because we say we use n buckets. Plus, how much is this thing here? That's 1 over also n times 1 over n, right? All those things are that. So I think it's easy to see that this is a sum. How much is the sum of n things of 1 over n? What?
1.
It's a sum of n things. Each one of them is 1 over n. 1. And how much? Maybe these are n squared things, right? Because it's 2 So the sums run over pairs here. So the n squared things, but it's 1 over n squared. This whole parenthesis, it's a sum over j of a constant. Right? Again, this is a constant, including the sum.
Yes.
And this, including the sum of pairs over n squared, it's also a constant. Like it's n squared things. Perhaps not exactly n squared, maybe it's just half of them, but it won't matter in terms of asymptote. It's n squared things, each of them is 1 over n squared. It's n things, each of them is 1 over n. So overall is sum of j. Now I use that many buckets, I use n buckets, so this whole thing is going to be nice, huh? So the average running time for bucket sort is linear. Okay. You should know this for practical purposes. If you sort a large number of values, you look at the distribution of the values, that can help a lot. Now, the next level of this would be, okay, can you do something intelligent if it's not uniform, but you know the distribution? Suppose I say the values are not uniform, they're Gaussian distributed, they're exponential distributed, Poisson distributed, then what? We don't do that, but at least if you think your values are uniformly distributed, many things in nature tend to not be uniformly distributed, but some of them tend to be uniformly distributed. It's easy to find examples of things that are Gaussian distributed, close to the mean, and close to the extremes. Can anybody give me a natural example of something that tends to be uniformly distributed? Are salaries uniformly distributed? If I look at all the salaries in the United States, the mean is about $40,000 a year. And the mean is like, I don't know, 5,000, maximum is few millions or billions. Are the salaries of people uniformly distributed? Or they tend to be close to the average? Close to the average, so that's not a good example. What is uniformly distributed? Natural example. Roll of dice. If I play a game and I'm assuming a fair die, those ability to get 1, 2, 3, 4, 5, 6 when I roll a die, or when I roll 3 dice, maybe it's uniformly distributed, right? So you got to think a little bit about this when you implement it in practice, whether it makes sense, the assumption or not. And if it does, you should absolutely use this method, but think about if it does or not. All right. Now we're going back to this. Here. So we've done this part, say, okay, here's how I can cheat the theorem. Not really cheating. Average case, it's linear, so that's very nice, right? It's easy to see it's optimal. I have to at least read the array, so that's linear. I can't beat the worst case in my theorem. That's still, actually, what's the worst case? If the values happen to not be distributed at all what I want, and I apply buckets, or what do I get?
In one bucket with many rows.
And then the runtime is? So let's write that down, worst case. But that's okay, like I said. In many cases, if we run this over your Google and run this by volume every day, you don't care about the worst case, you care about the average case. Because the average case is what's going to give you your electricity bill, not the worst case. So now, let's see how can we do not based on comparison sorts. This is still based on comparisons, right? Because inside the bucket, that selection sort or insertion sort was using comparisons. You could say these first steps are not based on comparison, particularly this one. We not do any comparison to assign the value to its bucket. This is kind of how the array random access works. By looking at the index, you know exactly in memory where to go read that value. You don't do any single searching. You know the index number 5 in the array is 5 times the size of the unit plus the offset. You go directly there, you read that chunk of memory. So how about counting sort? I think that's what he has in mind. He had in mind when he tried to answer that. Wrong file here. Here's what we can do. Instead of, this is not based on comparison, instead of comparing things, so we don't do compare. Instead, we do counting. So I'm going to start with an example because it's easier to see with an example. Here's my array. I'm going to write it vertical this time, but it's the same thing. So I have 1, 2, 3, 4, 5, 6, 7. This is the indices, and the array A is 3, 4. Sorry, 3, 4. Yeah, that's good. 3, 4, 6, 8, 4, 7, 3. So just like before, this is vertical instead of horizontal. Inside the box, inside A are the values, and the positions are outside. Here's what I want to do. I want to look at the values. So values depends of a range, like in this other procedure, bucket sort. I'm going to need to know the range. Let's assume the range is 0 to 9, for example. I'm picking this one because I want to build an example based on it later on. You can pick any range. Right? So 0 to 9 discrete. You recall my observation to his answer. What he wanted to do, count the values in the range, can happen if they're discrete. If I say a range with all the real numbers in there, you can't really count them because it's not like you can count the values of the hash. It's just too many possibilities in that range to count all of them. But if the range is discrete, this discrete we should emphasize, write it as big as you can and make it in red, okay? Has to be a discrete range to count it. So the solution is counting the possible values in range. So, which has to be discrete. And when I say the possible values, I mean all possible values. That's the two critical aspects of counting sort. I'm not only counting the ones I see, aka 3, 4, 6, 8, 4, 7, 3. Is there any value in the range that is not in my array? If the range is 0 to 9, do you see any value in the range that's not in this array? Does it have all the range values? What's a value that's not in here? 1. What's another value that's not in here? All those values, I need to count them too. Okay? So it's not enough to count the ones in the array. You need to count all the values in the range. So how do we do this? The values are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. This is the range. Remember, it's discrete. And here's the counts from the array A. How many zeros are there? How many ones? How many twos? How many threes? How many fours? How many fives? Sixes? 7? 8? 9s? How many people follow me here? So what I do? I count all values in range. Of course, when I say count all values, the ones that are not in my array will have what count? 0. So I can just start with an array of zeros for all possible values, and then just add on 1 for the values I see in the array. That's okay, but keep in mind that you're going to need those zeros. Now, if you use a hash or some fancy data structure, I'm not saying that you cannot implement it without keeping track of the zeros. Maybe you implement it in a way that says everything that's not in my structure, like a sparse structure, what's not in it, it's a 0. Fine. Just remember that you're gonna need to count everything. Okay, so I count those values, and now here's how I sort A. It's very, very easy. So I'm gonna have an output sort. How do you think that's gonna go? I look into these counts, right? I say how many zeros I have. Zero do what? Nothing. How many ones I have? Nothing. How many twos I have? Nothing. How many threes I have? So what do I do? Put 2 threes in here. 3 and 3. Right? Why 2? Because I have 2 of them. So I put them right there. I move to 4. How many 4s do I have? 2. So what do I do? Put them in. 4, 4. How many 5s I have? 0, so I don't do nothing. 6, 1, 6, 7s, 1, 8. Right? So the 2 3s, this is those 2 guys in here. The 2 4s are those 2 guys in here. This 6 goes in here. 7 goes in here. 8 goes in here. I hope everyone can understand this mechanic. It's very easy, right? Since I know the count of my values, I go through and I say, I know I'm gonna end up with it sorted because I go in sorted order over these values, right? So if I decide to put 2 3s, before the 3s I had the smaller values, if any, not in this case. And after 3s I only have bigger values. So this output will certainly be in order. And will contain exactly the values of the original array, right? Because if I had 1 6, the output will have 1 6. Okay? So how do we write this procedure? Like pseudocode. Let's write counting sorts. We're gonna need A, and we're gonna need the range. Say min to max, discrete. Let's assume for now those are integers from min to max, so we don't worry about the discretization of it.
Professor, what if we have values in like 10, 20 and billions also, or a million also? How do you decide the range then?
Well, that's not part of this procedure. You have to know the range. If you have values that are billions, but also 10 and 20s, your range is from 10 to billions.
You have to know the million.
Right, so that's a problem, having a big range. So we're gonna get to that in a second. But you have to know the range to do this. So how do we do it? The first part is the counting part. Really quick, how do I do this? I set up an array C of everything from min to max. This is MATLAB notation. It says all the indices from min to max. It's what? 0. And then I say for I equal 1 to n. That's the size of A, right? Do what? I have to count the value I see. So what's the value that I see? A of I, that's the value. How do I increase its count?
C of I.
C of that value is
Plus equal to I is plus 1.
plus 1. Is that counting the thing?
Yes.
Good. For loop. That's the counting part. Just count all the values. And keep in mind that I set up my 0 so that whoever's not in the array has a 0 count. Now, how do I do the writing output part? This arrow thingy. The book has a way of doing it with A, B, and C arrays that's super confusing. So if you read it from the book, you're gonna be like, oh, I knew counting sort before reading this. And now, like every time I read from the book, I'm like, maybe my understanding of counting sort was not correct. But then literally, every time I teach this course, I read the book and say, did I really know, guys? So I figured out, no, I really know it. So I try to write it down in a way that makes more sense, but it's less implementable. The version from the book is the way you write your code, but it's harder to think about it that way, I think. But if you do, that's fine. So here's what we're gonna do. We're gonna start with the position. So this is the output part. We're gonna start with some value position that starts at 0. That's the position in the output. So then I'm gonna go for, how did that go? How did we go? We go for every value, right? So for every value in range, from mean to max, right? Again, MATLAB notation, from this index to that index. What do we do? So now suppose I'm at certain value, suppose I'm at this value 2. Or better, suppose I'm at this value 3. I have another for loop here that says for some C that goes to 1, 2. So what happens? I pick the value 3. I did something with the 3 how many times? 2 times. So this is from 1 to count of value, right? Let's not say C because then we get confused. Let's say D. So for every occurrence of that value, I have to put it in the output. So I'm going to increase the position because I need to move in the output to the next position. Right? This is position in output. And then how do I put the value in that spot? Output of position equal to value. Right. Now these may look like 2 for loops, one into another. Naively speaking, how many values can I have there? A range, right? And how many counts can I have for that value? N. So if you are naive about this, you get range times n, right? But that's very naive. Because why? The sum of the counts have to sum up to n. So if you do it this don't naively, this is going to be all n time. But be careful, if you do it naively, you might get range. Let's say the size of the range, typically max versus mean if it's integers, let's call that k. So naive will give n times k, right? Because it's a for loops, one can be maximum k, that's the range. The other one can maximum be n. The total maximum counts of a value could be n. So naively speaking, you could get an upper bound of n times k. But that's not possible. This independent of, well, let's think about it. Is it really theta of n? In terms of the counts I'm looking for, if I get a 0 count, I don't do nothing. So it's really this execution of positions here. This will be theta of n, because how many times I'm increasing the position and output overall, and I'm adding a value? N times. I'm only adding the values from the original array. But how about this for loop? This for loop is going to have some values for which I do nothing. Which are those values? The zeros. So this for loop, even though the inside executes, this for loop executes exactly k times. Right? So some of this case, when I get a 0, I don't do anything. But for the other case, total, I do. So this is total assignments. But there is this for loop for which some of the case do nothing. So what's the overall running time? N times k or n? I say the total is n plus k. Think about it this way. There are k steps here. So that is k steps. For each step, I have to at least verify, check out the count. The other load for each I do something, overall for all of them, is total of n. So think about this way, I have k students, right? I'm going to go for a student, so that's theta of k. But only for the students that have bad grades, I have to talk to the registrar and tell them, hey, there's a problem here. Now for these students, overall, I do another additional load. Not for each one of them, but for all of those problematic students, I do a theta of n load. So what's my overall load? I have k units of time to go for every student. And then for the ones that have no problem, I do nothing. For the ones that have a problem, I have to call the registrar. What's the overall load here? It's n plus k. It's the initial k steps of just checking plus the overall work I have to do for the ones that need something. Same thing in here. I went through all the values, so that's k. Then for the ones that I need to put on, I put them on. Overall, that's not going to be more than n because I only put n values that were in the original array. Yes.
What if all the values are same?
What's going to happen if all the values are same? One count will be n, all the others will be 0. So I still go, I do counting, and then I go over all of them. For most of them, I do nothing. But for the one that's all the counts, I have to run a for loop. I only run the second for loop exactly once for that value. I put those values in. Who's with me? Counting sort. Very good. So remember that my pseudocode is written a little bit more explicit with this position so you know where you are. You can actually get this directly from the array. That's how it's written in the book. Now the running time is n plus k. Is this linear in n? In linear, it's linear in n. Is it linear overall? Depends the k. If k is fixed, obviously linear in n. Who can give me an example of a sort that will, for which counting sort will work really well? aka k is a fixed range, and it's not that big, right? That's the problem that somebody said with billions. What's the problem? I may have few values, n. You were talking about salaries, so there's only n people, 100 people, but the range of the salaries is into billions. So n plus k is going to be billions in that case, but I only have to sort 100 people. So for 100 people, I'm going to have a running time of billions due to the range. So if I want to sort 100 students or 100 people based on their salaries, would counting sort be good? No, because I only have 100 items and the range is gigantic. How about the opposite? What if I want to sort 1,000,000 people? So n is 1,000,000 by their age. What is the reasonable range for ages? 0 to 200. Say. There was a Russian guy who lived for 220 years, maybe. 220, fine. The point is, the range is a lot smaller than n, and it's fixed, right? So then if I sort 1,000,000 people based on a range of 0 to 200, that's going to be roughly linear because the 200 won't matter compared to 1,000,000, right? So when is counting sort good? When the n is much bigger than k. What if I have integers from 1 to n? So I know that n of them, like a permutation. I have all indexes from 1 to n. I know the numbers are integers from 1 to n, and I know the range is 1 to n. What would k be in that case? N. And this will be a linear in n, even if k is not fixed, because it's on par with n. So for permutations, when you deal with indexes, usually this is a good idea, because indexes are from 1 to n in that range. K is n. Similar with bucket sort, if you like. And then counting sort will give you a linear time. Yes?
Like in this particular case, when we are getting count as 0, we are skipping the step of the loop.
Right.
Right?
We
if
still
like-
do the initial loop, but we check it here. the 0 will get out of this 4 when I say 1 to the count of 0. There's no execution of this loop, right?
Right. So if we got a case where we are having every element is having a count of 2.
Every element
Like
in
there
the,
is no element which is not like which is having a count 0. Every element is having some count.
yeah. So it's no different. Let's say 1, 2, 3, 4. Let's say I have 2 3s, 2 1s, 2 5s, and 2 4s, right?
No, everything from 0 to 9 I'm having everything twice.
Right. So let's say from 1 to 5 I have 2 2s here. There's no be a problem. I have the values 1, 2, 3, 4, 5 range. 2 2 2 2 2.
And plus
I'm going to say for all the values. So start with the 1. I have 2 1s, 1 1, 2 2s, 2 2, 2 3s, 3 3. So this will be executed k times the range. These 4 will be twice, will be 2 for each.
n plus n, k plus k.
Still n plus k. This is guaranteed to be n plus k all the time. Now I want to add something to it. I don't want just the values. When I sort, I want to keep track of the original indexes. So I want to add here the A original indexes. That is, I want to say, okay, these 3 here. This is the value from the array. What index was that in the original array?
Okay, 1 1.
At index 1, right? How about these 3?
1 7.
How about, yeah, 1 7. So this 3 is 1. How about this 4? Where was this 4? Index 2, right? How about this 4? 5. What is 6?
6, 4.
Now this, of course, has to be a permutation of 1 to n, right? Because the same index is just in a different order. When would this be a stable operation? So the idea of stability, I'm bringing this back from quicksort last time. There's 2 trees in here. If I only show you the output, you won't be able to say stable or not stable because you don't know which tree is which one. Every sorting method that works correctly would swap small values with big values to put them in order. Stability does not refer to that. Stability means if I didn't have to swap some values, did you swap them? That could happen for a big value and small values. No. Big values and small values will never be swapped because they either in correct order. If they're correct order, will never be swapped. If they're in correct order, they have to be swapped. What about 2 values that are the same value, like those 2 trees? Correct output can be obtained by keeping them in the original order or swapping them. But if I show you the indices, I'm not outputting just the sorting array. I'm also outputting the original indexes. A lot of MATLAB functions, Excel functions, so that give you that functionality, the permutation of the original indices, so you can keep track of it. If I have this output, would this be stable?
Yes.
Are the 3s and the 4s in the same order as the original? If you look at the indexes 1, 7, are they in the original order?
Yes.
How do I check the original order? What's the condition?
The first one.
They're in increasing order. If it's 1, 7, it's the same like in the original order because what's the original order? 1, 2, 3, 4, 5, 6, 7. Right? So if this is 1, 7, how about the other one, 2 and 5s?
Original.
Right. So this is stable, both of them. Stable. But can you do this? How do you know you put them in the correct order? So when you put those trees, you don't care about the order, right? You see 2 trees, put them in. Right? But it's no order in there. Suppose I'm asking you to output this too, or instead, if I have the array of indices, I can immediately get the sorted values. How can you do in counting sort producing this output? Not just the sorted values, but the original indexes permuted. What would I need here? So, yeah, so suppose I have this array A, right? Let's imagine counting sort. I don't have time to write it again. I do the counting part. I get to the output part. I get 0, 0, 0, right? 2 3s. That means 3 and 3. Now what about the indices? How do I decide 1 and 7?
Take the first occurrence.
What, I go through the array? That will be expensive, I think, to start going through the array to see where the 3 is. I think I need to keep some sort of list. I need another preprocessing step that says R3, value 3, the indices are, so here where the value is, I don't just keep the 2. I need to keep a list that says what are the indexes? 1 and 7. And at 4 I keep 2 indexes which are 2 and 5. When it's 0 I don't have to keep nothing. This is in position. This is in position. This is in position. So now I output the 2 3s here, and then what? I go in this list and I will put 1 and 7. Who's with me? Hands up. This is a great interview question. I say counting sort, the potential employee, that'd be you, light in their face, I know that. Right? And then the next question is, can you sort the indexes? It's easy to mess it up. Yeah, because that's essential. The stability of counting sort is an absolute essential property. Because we want to do one more in the next 8 minutes. The one we want to do is based on counting sort, so we're going to need counting sort and we're going to need stability. Stability is going to be essential. This is invented by IBM a long time ago. Radix sort. So it says sort by each digit stable. So here's how radix sort goes. I'm going to put a bunch of numbers. This is 1, this is the array. 1, 2, 3, 4, 5, 6, 7. These are the positions. And the numbers are 4, 5, 7. These are integers, but it works with any representation. 6, 5, 7, 8, 3, 9, 4, 3, 6, 7, 2, 0, 3, 5, 5. So now this is the array input. I'm going to sort by most important digit. So essentially I'm sorting by the first digit. Now I'm sorting like in Excel. I'm not just sorting those digits by destroying the values. If I swap 3 and 4, I don't have the same values. What I'm saying, I sort the whole array based on the first digit. So if the 4, this 4 is smaller than the 8, when I swap, I'm not just going to swap 4 with 8. I'm going to swap 4, 3, 6 with 8, 3, 9. Just like in Excel, when you say sort by this column, it doesn't destroy your record. It sorts, it rearranges the whole record. So you can think of it as Excel sort. So how do I do that? If I sort by the first digit, what's going to be the, again, it's stable. So I have, what's the smallest digit here? 3. There's 2 3s. So the top will be 329. Remember, I keep the order if I don't have to swap. 2 3s, so those would be 355. What's the next digit that I have? 457. 436. Those are not in the right order, but why are they in this order? It's a stable sort. They don't have to be swapped if we sort by the 4, so they are not swapped. What's the next one? 6, 5, 7. What?
720.
839.
What? 839?
No.
Okay. Then I would need to do what? Sort by second digit. How would that look like? What's the first one? What's the smallest first digit?
2.
What's the next one? What's the next one?
839. 355.
What?
657.
You think I'm gonna get it sorted that way? Why not? Somebody with an idea, so my notes are correct. We started leaving the wrong foot. So I think the idea works, but we got it wrong something. Somebody has a clue why we got it wrong here. Yes?
We need to start it from the units.
We need to start from the other digit. Right? So, let's see, how would that look if we start from the other digit? So I'm sorting by, not the most, but the least important digit. How about now? Still stable sort, because I'm using counting sort to do this. What's the sorting by the last digit?
720.
Yeah?
355.
Sort by the last digit, right? 457. 839, right? Now I'm sorting by the middle digit. So what's going to happen here? 720, 436, 355. 1, 2, 3. I think I messed up the spacing. 329, 436, 839, 355. What's the next one? 457. So the important part here, everybody can sort by the middle digit, is that if the middle digit is the same, as in what? Say 5 and 5, right? Then the order remains from the previous sort. So if I have the same digit for the tens, I need to remain the sorter stable from before, which was already sorted is 5 versus the 7. Because otherwise, I sort the tens, but I lose the unit sort. This way, if they need to be sorted by the tens, then I don't care about the units. But if they're the same unit digits, I need to keep track of the previous sorter. So the last step is sort by the 100 digits. I get what?
329.
329?
355.
Yeah.
437. 657. 837.
I think everybody can see this is sorted. The critical thing is that it's stable. So a digit, as I move from right to left, a digit k, it doesn't swap unnecessarily. So if I have the same value, I keep the previous sort. That's why when I have the same digit 5, I have the sort from before from the units. So in other words, if I have the same hundreds and the same hundreds, now it depends on the tenth from before. If I have the same hundreds and tenths, it's all the way from the first sort that it worked out correctly. Now, how long is this? Each one of them is a counting sort, right? Each sort by digit is counting sort. Why is counting sort so applicable here?
Digit 0 to 9. 0 to 9 is
The range for each digit is, so each counting sort will be how many elements I have
the scale to be
plus the digit range. And how many times I have to apply counting sort?
number of
Times the number of digits. Because I sort for each digit. Now the thing is with computers, you can choose the digits. What does that mean in normal English sentence when they choose the digits? Like what if I don't like digits from 0 to 9? What do? I can change the numeration base. The values are the same, right? These values I can represent in octal or hexadecimal or binary or whatever I want, right? It doesn't change the values, it just changes the representation. So what's the trade-off? If I choose hexadecimal or a high base, what's going to happen with the number of digits? Decrease or increase? Decrease. What if I pick a base like base 2? What's going to have a number of digits? It's going to be long. But on the other hand, what's going to happen with the digit range? If I pick a base 2, how much is the digit range? 2. If I pick digit 16, what's the digit range? 16. So there is a question here. What's the optimal digit range? You want this to be small, right? N is whatever it is. It could be 1,000,000 points. But the question is how you represent into digits to get the minimum, right? If it's decimal, so let's say here decimal. Decimal means what? N plus 10 times log base 10 of n, right? I think.
yes.
If you or max value. Let me write this on a different, because this is important. Last thing we're going to say today. So let's choose digits on b bytes. So each digit has b bytes. Base 2 means what? Bits, sorry. Base 2. So base 2 means b equal 1. Base 2, every digit takes 1 bit. How about base 16? B is 4, right? So now, what is the digit range? If I use b bits. How many possibilities are on b bits? In base 16, how many possibilities are there for a digit? 16. So in general, what's the digit range if I choose b bits? It's from 0, 0, 0, 0 on b bits to 1, 1, 1, 1 on b bits. So that's roughly is, how many possibilities are there? 2 to the b. In base 2, that will be 2 possibilities. How about the number of digits to represent max? So I have a max. Somebody tells me the maximum number of items, maximum value is going to be 1,000,000. It's max, it's log base b of max, right?
Yes. Plus 1.
Maybe plus 1, but this is an asymptotic notation, plus 1 would matter. So I'll stop here. I'm just going to say, based on this, you can compute the running time by choosing the proper b. How many bits do you want per digit? If you choose 2, you get a function. If you choose 4 or 8, you get a different function. That's not so critical. The critical part is for radix source to work, we need stability. Counting sort is very, very suitable because the range is very fixed and it's stable. Okay, that's what we have. I think we're done with sorting. next time we move on to greedy algorithms. But there's another homework for sorting. So there's one which does the initial side, and then there's another one that does the sorting in linear time. I think that's already available, right? Homework 3. If you have questions about your grades, we're going to have a script that you can see the grades online. But for now, you can just ask the TAs to show you your grades. The TAs have office hours primarily dedicated to discuss grading with you. Did you guys get any feedback on Dropbox on your problems? Right? Okay, so if you have questions about that, if you don't have questions, you don't have questions. But if you have questions about that, you come to office hours, ask the TA why I lose points here. That's not very important. Homeworks will not be critical for your grades. In fact, they won't matter at all. The important part is for you to know what you did wrong. Okay? The point of the homeworks is that if you cheat, all those problems have solutions online. I know that. We're going to know you cheated the exams. Every single person in the last 10 years who got a B+ or higher overall grade got 100% of the homeworks. So there's no way you're going to cheat on the homeworks or don't do the homeworks and you end up with a good grade at the end. Homeworks are designed as practice for the exams. You should know what you do wrong, and you should not look at the answers. I don't care if you look at the answers, honestly. But you're cheating yourself because by not doing the problems, you don't have the practice, and then you're going to get stuck in the exam. So if you have questions about this, you should try to find me Monday, Tuesday, Wednesdays primarily. You can ask the TAs, but finding me is better, and ask the TAs mostly for grading. If you want solutions for this, we can print them. I don't have all of them, but I have most of them. We will not give you PDFs electronically or post on the web, but we could print solutions for most of the exercises and hand you the paper. Here's the solution. We don't want to be that obvious as putting the solutions online, although I'm sure they're very easy to find. This book is printed in 200 languages, so I'm sure you guys have it by now. The solution manual is also printed in 200 languages.